Hello, my name is Eugenio. I work for Red Hat. This is Hanna, which also works for Red Hat. And we are going to present the IOMMU work she's developing in rust-vmm and how this enables new use cases for FUSE and vDUSE. So the first part is the motivation of this work. And it's being used in the artificial intelligence workload. So at this moment, the way artificial intelligence uses FUSE is to mount remote files, the remote artificial intelligence models, as local file system. These are the typical advantages that the artificial intelligence workload is able to access these files seamlessly, like standard write, read, syscalls. It doesn't need to handle things like load balancing, how to access the different cloud providers for these files, etc. But at this moment, FUSE is not super efficient. FUSE needs syscalls or IOPTers against a character device. And yeah, this can be a little bit slow. So we plan to accelerate all of that. So you have here a picture, a diagram on how this works. You have the workload that access the files for the workload. Those are files of Linux virtual file system. This virtual file system goes to the FUSE kernel module, and then this FUSE kernel modules uses syscalls to access the FUSE device, which translates these syscalls to whatever. For example, accessing remote files. In order to not put here any kind of vendor, we are going to use SSH file system, but it could be a FUSE device to access, I don't know, Azure, Amazon, whatever. So the main objective is to remove these syscalls to use something more efficient, but all the artificial intelligence workload needs to work the same, needs no change. So the artificial intelligence workload will still use syscalls to access the files. So this is the main mission, and we have a few alternatives to doing it. One of them is to directly, is to use virtio. To do it, virtio works with virtios, which are asynchronous, can batch, etc. So no syscall involved at first sight. So it could match the target. With vDPA, you can also expose the FUSE system to virtual machines with vhost-vDPA. But if you want to keep the workload exactly the same in containers, you can also use virtio vDPA. Okay. And the other part of the architecture is vDUSE. vDUSE allows to implement the device in userland. So we can export this userland device again to either virtual machine or containers. So this is kind of the final picture. Let's say all the control plane goes to the kernel. Again, the artificial intelligence workload is not modified at all. It uses the file system syscalls, which gets routed through virtiofs, and this uses a virtio, which is the virtio data plane, to this device to create, manage, etc. We use vDPA and vDUSE. So here's kind of a summary. One option we have for that is to modify virtiofsd to integrate all of that capabilities, which are to be able to act as a FUSE device that gets the files remotely and is able to expose to the kernel through virtio. To do it, we could implement each cloud storage, Amazon, Azure, etc., in virtiofs, but this is a little bit tedious. At this moment, it's planned that NFS will get integrated in NFS, so we could add all of that code as a backend, or we can make virtiofsd to be able to run actual FUSE devices, which are already in the wild. But this is, again, something planned. To export it through vDUSE, we could also implement vDUSE in virtiofsd, which probably involved to create Rust crates for that, etc. Or another idea, to be a little bit more generic, is to use a bridge, to use a vDUSE to vhost-user adapter, which converts all the control plane from vDUSE, which uses syscalls or ioctls against a character device, to vhost-user, which, as Stefano mentioned, works through a Unix socket. So at this moment, virtiofs, for example, works through a Unix socket, through vhost-user, which is a Unix socket. And the plan is to convert all of that to the vDUSE protocol. So it gets routed through the kernel, and the artificial intelligence workload see no difference. Again, repeating a little bit, virtiofs plus vDPA allows us to not to change any kind of artificial intelligence workload, and the bridge to use allows not needing to change that part of virtiofs. This is very generic. We could expose other vhost-user. For example, the device I'm working with at this moment is DPDK, and it works. So we could export all of the already existing vhost-user devices, which is cool. But at this moment, vDUSE depends on IoTLV misses, which is not implemented in all the Rust crates that virtiofs uses. So Hanna is going to extend a little bit on that. But at this moment, well, just want you to know that there exists a bridge which could connect vhost-user devices to vDUSE system. And yeah, basically, this will be the previous scenario. So another option we already have working is to adapt libfuse to expose itself through a vDUSE device, not as a regular devfuse character device. That control plane looks like this. All of these modules are involved. As I mentioned, virtiofs to route all the VFS calls, vDPA to expose the vDPA device to the host or to the container, vDPA, vDUSE, and then the library uses vDUSE directly. And the data plane is totally direct between virtiofs and the application. So this has many advantages. All of the FUSE devices works or should work. I have not tried all of them, but in principle, all of them should work. And as a disadvantages, at this moment, the FUSE devices are not really thought on all of these, let's say, batching, etc. The introduction of IOMMU may change it, and it might make it simpler to introduce all the virtual data plane there. A proper and a fair comparison should be done for performance, etc. But at first, one of the main advantages, as Stefan mentioned in the previous talk, is that IOMMU is not allowed in all the containers environments. But this vDUSE attack surface will be way, way smaller, only file system calls. So it should be more easy to allow it. And yeah, another alternative similar to this will be to make virtiofs act as the libfuse, let's say. So virtiofs exposes the fuse device through vhost-user, and then the bridge converts it to the vDUSE calls. So that's the current two approaches we have. Just for all of you to know that it could be used like a lot. No, Hanna.
This works. Okay, sounds good. Okay, so let's get back to IOMMU. Because the thing is, we need it for virtiofs anyway, because there are some VM guests that just want all of their devices to run with an IOMMU, and that includes the virtiofs device. So we are going to need to implement it in the rust-vmm ecosystem no matter what. First, let's talk how guest memory works with vhost-user specifically and the VM memory crate. So you have your guest as a physical address space that's split into multiple regions. And when the guest wants to point to anywhere in that memory, it uses a physical pointer. We call that a GPA, a guest physical address. And all of that memory is owned by the VM hypervisor, which, for example, could be QEMU. And then it's also shared with user devices like virtiofs, so they can access the guest memory. And so when virtiofs wants to resolve a physical pointer, a GPA, it does so by looking up the region in memory, in the guest memory, which it can do, where the pointer points to, which it can do because all these regions are annotated with the GPA range they cover. So it looks up the region, looks up the offset within, and then there's the data right there. These accesses are facilitated by the guest memory trait in the VM memory trait. For example, it has a get slice function where you put in a pointer and a length, and it spits out a slice to the data. And then you can read from that slice or write to it however you want. There's also a higher level trait called bytes, which has higher level interface. So you can use this to read and write structured data or load and store doing atomic accesses. And the differentiation will become a bit important later on. So how do things change when we add an IOMMU into the picture? Your device is now put into a virtual address space. And so when the guest wants to point to anywhere in memory for the device, it uses a virtual address, an IOVA, IO virtual address. And when the device wants to access the data behind that IOVA, it has to go through the IOMMU to get access to the data. What changes for virtiofs as a user device is that it no longer sees all of guest memory necessarily, but only parts of it. And these parts are also no longer annotated with a physical address, but with a VUA instead, a vmm user space address. And this is actually a pointer into QEMU's user space address space. So this means nothing to virtiofs, and it means nothing to the guest. But when we encounter an IOVA, what we can do is ask QEMU where that points to in its own address space. So QEMU will send us a VUA back, and then we can use that just like before to look up the region and the offset with it. Now, of course, asking QEMU every single time for every IOVA that we want to access is very slow. So we have a cache for that, a TLB. And so we only need to communicate with QEMU on TLB misses, basically. And this communication works through the vhost-user protocol. Specifically, this consists of two Unix sockets often. So we have a front-end socket that handles requests from QEMU to virtiofs, and the backend socket for requests the other way. So when we have an IOTLB miss, we send an event on the backend socket, and hopefully we will get an update for that address on the front-end socket back, so we get the translation that we've been missing. How do we get this implemented? This is our current design that we have, which is you have your device emulation, like virtiofs, for example, and it wants to access guest memory, so it has to have the physical address it wants to access, puts this into some guest memory object, and out comes the data. With an IOMMU, things change. You now have a virtual address, and the guest memory object will no longer understand physical addresses or IOVAs, but only these VUAs instead. So we need a translation layer in between, and of course, that translation layer is an IOTLB backed by an IOMMU proxy that communicates with QEMU through the vhost-user protocol. Now, another thing that we'll have to change is that when you're accessing physical memory, you just need a pointer, basically. But with virtual memory, you also need to say, do you want to read from this, or do you want to write to it? Remember, the get slice function gives you a slice with what you can do whatever you want. But now you will need to specify whether that slice should be readable or writable or both. So all the device emulation code will need to be changed to pass this access mode. And finally, of course, these loose tiny bits all need to be put into some nice box so that they get a common interface that hopefully is kind of similar to guest memory, so the changes will be kept minimal. So we need to implement an IOMMU proxy and an IOTLB, and we need to add these access permissions. Now, luckily, we don't need to add them everywhere, actually. We only need to put them into places where the guest memory interface is used directly. Where the byte trait is used, we do not need to change anything because the methods of the byte trait are called read, write, load, and store. So you see a pattern there. You already implicitly have the access mode right there. So the users already passed the access mode they need. So everything's great. Another thing that changes is memory fragmentation. So with physical memory, you could be reasonably sure that when you're passing, when you have a continuous slice in physical guest memory, it would also be probably continuous in your own user space memory. But not so with virtual memory, because every single page may be mapped to some completely different place in your own address space. So of course, when you're passing the page boundaries, you might encounter an incontinuity, and so you get fragmentation. So a single slice in virtual I/O memory may correspond to multiple slices in your user space memory. Okay, so how could the actual implementation look? Now, This is all, of course, subject to discussion still, but this is the current draft that I have. The idea is in the VM memory crate, we would introduce a new trait called IO memory that is similar to guest memory, but not exactly. And specifically, so the idea is basically where guest memory can only handle physical memory, IO memory will be able to handle both physical and virtual memory. So the interface needs to accommodate for this access mode first, that it always asks the caller, the user, for the access mode. And second, the get slice function that returns a single slice can no longer really work. Will probably be a get slices instead that returns, for example, an iterator over multiple slices. Then this trait needs to be implemented in something, of course, specifically an IOMMU memory type that encapsulates a physical guest memory plus some abstract IOMMU translation layer on top. Now it's left completely abstract in the VM memory crate because we'll be dependent on vhost-user stuff. So of course, has to go into vhost-user crate. So we'll come back to that later. And because the IO memory trait is supposed to work on both physical and virtual memory, we need to make true on that promise and implement it on all existing physical guest memory types by having a blanket implementation of IO memory for all of these types. This will then also allow our users, hopefully, to switch from guest memory to IO memory. So they will also get the ability to handle virtual memory. And to make that easier, we can implement and should implement the bytes trait on top of IO memory because we can, because we know the access mode, and because it will make changing easier. So such users that need to switch over are, for example, the vhost and all the VM virtio crates. So they don't need to implement anything new, really, but they will need to switch away from guest memory to IO memory. And in every single place where they use the bytes trait to access memory, they can continue to remain completely SDR, which is great because those are a lot of places. And only in a few places where they use the guest memory interface directly, they need to be changed, as we've seen. Like they need to pass the access mode, and they need to deal with memory fragmentation. Finally, the vhost-user-backend crate is a place where you actually do implement the IOMMU, the vhost-user-IOMMU. Nothing really surprising here. It's an implementation of the IOMMU trait that communicates with QEMU through the vhost-user protocol. Another thing that changes, or that will have to change, is that vhost-user-backend currently prescribes a specific memory type to its users, which is guest memory mmap. So you, as a user, you cannot use any guest memory, but you have to use guest memory mmap. And this is a purely physical memory type. So this requirement would, for example, be relaxed by having a trait, and users can then choose which type exactly they want to use, whether they want to continue to use guest memory mmap or the potentially virtual memory type IOMMU memory, wrapping around the guest memory mmap and a vhost-user IOMMU. What does this mean in the end for virtio as an example binary? How do we, after all these changes, get support for IOMMU in virtio? We, of course, update the dependencies, obviously. Then there's a get slice call. We need to fix that. There's always a get slice call. Third, enable the IOMMU feature, and specifically for the vhost-user-backend crate, that's a breaking change because now we need to specify which memory we want to use. But we just do that. We specify guest memory mmap because it's what we always used. And then immediately we switch away from that to IOMMU memory. And that's all we need to do. Then we can already enable the feature bit on the IOMMU platform bit to let the guest know that it can use an IOMMU and that we will be happy to work with IO virtual memory. So great. What's the catch? I think memory accesses are supposed to be fast. Now, the problem is that when you have an IOTLB miss, you will have to deal with 4 vhost-user Unix, 4 Unix socket messages. We just heard about syscalls. So 4 Unix socket messages, I don't think are great for a memory access and would be better if we could do without. The second thing is potential deadlock problem. Can actually go into detail, didn't expect that. So there are 2 problems. Specifically for rust-vmm, the problem is, say you have a device driver and it does something with the vring, and around the vring there's a mutex, and so the device driver locks that mutex so that it can process the vring. Then during this operation, it encounters an IOTLB miss. So that IOTLB miss will have to send a message to QEMU and then await a response on the vhost-user Unix frontend socket. Now, what happens if your concurrently processing a completely different vhost-user operation from the front end that may need to modify vring, like a set vring call message, while you get a deadlock, because now this operation will try to lock the vring, cannot do that because it's currently locked, and the lock will only be released once the IOMMU message comes in, which will never come. That's a specific rust-vmm problem. I don't think it's really easily to solve, however. And the other problem is, in general, the vhost-user protocol does not allow you to process multiple messages concurrently. So even if you just have an IOTOB miss while you are processing a vhost-user operation, you have exactly the same problem, basically. So it's inherent to the protocol. And I think the only good solution to this would be a protocol extension, so that you could have a bypass for IOMMU messages. I think they're really critical, and I don't think they belong in with the other vhost-user messages that we have. So it would be good to have a bypass, but I don't have any concrete ideas on how to do that yet. It's perfect, because we're at the end of the talk, and so we're happy to take your comments and questions. So you mean like basically having guest-to-guest virtual devices? So I know Herman has been looking into that. I don't know whether you know anything about it. Well, but I know it's an idea at least that has been run, yes. Herman, do you want to say something to that?
No, you'll be host. Sorry.
He said there's an issue upstream. Okay, thank you.